have the second set of lectures by Hollands about operator algebras, entropy, and graph.
Yeah. And today will be mostly about quantum information. So I'm going to continue to tell you a story. Going to continue with quantum fields in curved space-time. So I haven't really talked about any concrete curved space-times, but I'm going to do so now. This is supposed to represent a Rothschild. Am I talking loud enough? Supposed to represent a Rothschild with space-time. So again, I'm going to assume that you have some familiarity with general relativity. It's not going to be very complicated. With general relativity and the metric is this f is 1 minus r plus is called the Schwarzschild radius, and in these coordinates we cover the so-called exterior region of the space-time. As you can see, if you this is a space-time which has a Killing field. It has also some rotational symmetries, which are so important. So the first thing, one thing that I told you last time is about defining states. On this geometry. So there are a couple of interesting states that people consider. So I'm going to consider the so-called Hartle-Hawking state. Hartle-Hawking. So the Hartle-Hawking state is defined as follows. So I told you about one trick to get states, which is the weak rotation, or more properly, analytic continuation. So the observation to make here is that you can set t equal to I tau. If you do that, then obviously there is no t in any of the components. So what that only will do is that you get a plus instead of a minus in front of here. However, you have to be a little careful because this vector f goes to 0 when r goes to r plus. It reflects that the norm of the Killing field component is 0 when r is r plus. And the picture that you will have seen is this, therefore. So these are supposed to be the orbits of the Killing field. And where the Killing field becomes null is where r is equal to r plus. So this would be, in this drawing, actually both the future and the past horizon. Assuming you have this familiarity with this Penrose diagram and how it's connected with these observations about f. Anyway, so if you do the analytic continuation, you have to be careful in that this component goes to 0 and this component goes to infinity. So what you can do, although I'm not doing it carefully here, what you can do is you can take out 1 over f from the metric, or you can kind of get rid of the 1 over f by going to a new r coordinate here. And what that basically does, it gives you, by comparison, a dr and an f squared dt squared. So that would be the ratio between these components. And the observation is then that you should compare this with the metric of flat space into Euclidean space. As you know, that would be actually r squared I squared. Write it in polar coordinates. And the analogy is that also this coefficient goes to 0 at the origin. So rather than thinking of this tau as some coordinate ranging between minus infinity and plus infinity as t, you should therefore think of it more like a coordinate multiplying a term that goes to 0, so you should think of it more like an angle. Yeah? And so the periodicity of phi ensures that this is a smooth metric. Yeah? So you have to impose the periodicity, a 2 pi periodicity, otherwise you will have a conical defect. Yeah? So maybe you can think about these considerations. Anyway, if you require that the analytically continued metric Euclidean metric to be smooth, and when r is r plus, we must impose that tau is identified periodically with some period beta, and beta is the inverse of that Hawking temperature. So you can from this consideration, you can actually find what this temperature is. Do you know what it is? Maybe that's an exercise. Yeah, so you find the temperature by supposing that this is smooth. Yeah, so you have to figure out what's the periodicity. So if you get this with some constant here, then the periodicity would not be 2 pi, but it would be related to this constant. Yeah? So with that you can figure out what the Hawking temperature actually is. So that's the so-called Hadl-Hawking state. So that gives the pure mixed state. And then back to the thermal equilibrium. Hawking temperature. And so maybe one question, what is there has a higher Hawking temperature, a small or a large black hole? Maybe that's good to know. Touching black holes is not great anyway. It's a very small black hole, it will just pierce you. Create a very small tunnel inside you. So dangerous. Larger one. Like swallow you. But, maybe you can think about that too. And so anyway, it gives a mixed state on the exterior region. Exterior region is this region here. Now, you can actually think of this space-time as really the double thing. That's certainly nice mathematically. That's called the Kruskal extension. So this is kind of an identical copy of this in a way, or a reflected copy, where though the killing field, the analytically continued killing field, the orbits would be going down. And so if you draw it this way, you will see, and you also may be drawing the orbit of the killing field inside. If you look at this little piece, then the picture here of this little piece is that you have boosts going this, orbits of isometries going this way, and as Bill Unruh noted in the 70s, that's just like windless space, yeah, just like the situation with wedges. And so he got the kind of idea that this, to look at really this Hawking effect, or the physics of the Hawking effect just in windless space, just in flat space, a brilliant thing, and he found the Unruh effect. And so, but it's this kind of observation here that d by t is locally, so this is called the bifurcation surface. D by t is like a boost. And then you got a state with a mixed state at the Hawking temperature. So this suggests that if you look at the state for the whole, look at the operator algebra for the whole space, maximally extended space-time, that will be a pure state. So this is pure state on the Kruskal extension. Such that the reduction of the states, or the restriction to, let's say, the right half, I'm going to call it a wedge, although it's not really a wedge, I'm going to call it a wedge. It's the Hawking state. So this pure state is sometimes called the, well, I'm going to call it also still the Hartle-Hawking state, but people sometimes, for some reason now, call it the thermofield double. Yeah? It means you, so here, in this space-time, really there are degrees of freedom that are geometrically associated with the region behind the throat. But if you just have a thermal state in a box, you can still define this double to make the state pure, but then these extra degrees of freedom are just invented. Yeah? So don't exist like here exists. Yeah? So this is called also the Hartle-Hawking state. So you can say in a way that if you talk about density matrices, which of course is illegal, this is the right wedge, and this is the left wedge, and this is the wedge. So if you trace out in a way, if you trace out over the right wedge this Hartle-Hawking state, and you get the density matrix, if you like, that corresponds to the Hartle-Hawking state, the mixed state in the right way. And so that's here, and as my other colleagues explain, to capture this correctly, this Tomita Takasaki modular theory, so you don't have to actually talk about things that don't exist. But if you pretend that they exist, then you will get here this get a kind of a density matrix, because it's a thermal state. Its density matrix should be like a Gibbs-like formula, and K would be the Hamiltonian. Rho. So if you like, so this would be the integral over mu. I'm not sure this is a good notation. I'm going to call the stress energy tensor theta mu in this lecture, actually. That's okay. It's not a convention in general relativity, but otherwise I'm going to get confused with other things that I call T. So formally, this is the formula for the reduced density matrix. It's just supposed to express that it's a Gibbs state with respect to boosts, and the boosts are generated by this, and this is the Hamiltonian for boosts. Okay, so these are some more heuristic formulas that, and the machine of operator algebras gives way to make this rigorous. So the problem always is in these heuristic formulas is what really happens here at the interface. And I told you that quantum fields, and this would also apply to the stress energy tensor, they are distributions. So you can smear them, that's fine. But what you smear them with has to be a test function. Now, the problem is that what you smear this with is kind of a step function, which, well, it's only over 3 dimensions in the first place. That's not the big problem. But the problem is that the integral abruptly stops here. So what you're smearing this with is not really a smooth test function, but a window function. Yeah? And the window function has a sharp edge, so it's not a test function. So a distribution does not like, in general, with this, and so it will show its singular nature, and that's precisely what ruins this formula if you want to take it seriously. And what you always have to do is, as Roberto and Gerardo will have explained, you go to the modular operator, which is kind of a combination always of the left and the right things. And so it's such a combination that these these problems at the interface, they kind of cancel each other out.
But I ask you, if you do this combination, then it has access to the interior of the black hole, right?
Still, yes, yeah. So yeah, you can look at what the Hartle-Hawking state looks like here. So.
You cannot.
You can.
You can?
Yeah.
With this modular Hamiltonian.
Oh, the modular. Oh,
yeah.
With the modular Hamiltonian, no. I mean, if you want to see, you would have to evaluate the stress energy tensor. But not the modular Hamiltonian, in a way, is
right.
So it's somehow in there, but as you say, that the orbit is going this way, so it doesn't carry an observable towards the singularity, so the modular flow doesn't probe the singularity. Okay, so this is the Hartle-Hawking state. I just want to mention that for completeness. And there are also other states, well, many other states, but other states that are often considered in Schwarzschild. So this is the, I'm going to call it the Rindler vacuum. The Rindler vacuum, although in Schwarzschild it's called the Bulwer state, but I'm calling it the Rindler vacuum. Bulwer was a student, I don't know, in the 70s, very nice papers, and disappeared from this branch of science at least. So what's the Bolwer state? The Bolwer state is the following. You can, if you just restrict yourself to the exterior, and you're in the Lorentzian picture, then you can imagine that you're going to look for a state at a different temperature than the Hawking temperature. So you can imagine that this will not have a nice Euclidean counterpart, because then the Euclidean, the Wick-rotated metric is not smooth at the horizon, but if you just increase it at the outside, maybe that's not a big deal. And the Rindler vacuum is kind of the ground state. In a way, of this K, this boost Hamiltonian. So you can do that, and it's not in the terms of operator algebras. This is not a normal state. On the wedge algebra, meaning that it's or if you say it cannot be because it's supposed to be a pure state, and I don't know, Roberto or you have talked about a type for Neumann types. The algebra of the exterior is a type 3, and type 3 algebras simply don't have any normal pure states. And so you can already see from this just very general perspective that this data is going to be something funny with the state. It's a non-normal state. So it's GNS representation gives a type 1. And so this is the Bolwer state, and there's another one. This is the state. So the Bolwer state is where the temperature is 0. Of course, you could take any other temperature, but that would also be which still will not be a pure state, but it will also not be a normal state. So what's the Unruh state? The Unruh state is the state where you impose you define it somehow by the initial conditions for the two-point function. So the two-point function for a free scalar field is a solution to the wave equation in each entry. So write it like this. Two states. So in Gaussian state or Gaussian state. So you have to define somehow this, and I'm telling you that you define it with regard to in terms of its initial conditions in x and x prime simultaneously, or you could define it in terms of modes. And the modes are made in such a way that the restriction of the state to this hypersurface is a null surface. And that will be the same as for the Hassel-Hawking state. But the restriction to this null hypersurface, square minus, will not be the same as the Hassel-Hawking state, because otherwise the whole state would be the Hassel-Hawking state, but it would be a state at 0 temperature here. So it's a kind of a state which does not really have a definite temperature. It's not a thermal equilibrium state, but you think of it as it's a bit like in a CFT, a two-dimensional CFT with just left and right movers. If you put the left and the right movers in states at different temperatures. Let's say you put the right movers in the vacuum and the left movers at some non-zero temperature. That's like an Unruh state. So it curves this 3 + 1 dimensional space-time. Of course, the general solution is not a superposition of left and right, and not a sum of left and right movers, but it's kind of like that. Running state, so this is like a steady state. It's stationary, meaning that it's still time independent, but it's not a KMS state. In fact, in some definition, it's a steady state. If you want in the algebraic language, the formulation of steady state, to my knowledge, was first proposed in a paper by myself some time ago. Look up the title, I forget. Okay, so this is the picture of Schwarzschild space-time, and what I want to emphasize is that it's the close analogy to the Bisoniano-Wishman setup that we described. Now you could ask, there are, if you have taken maybe an advanced GR class, you will know that there is a rotating counterpart of this black hole space-time called the Kerr metric, and interestingly, for the Kerr metric, there isn't an analog of the Hartle-Hawking state, and there isn't a straightforward analog of the Bisoniano-Wishman theorem, and I'm not sure myself what exactly to think about that, although I'm sure there's a resolution to this. Okay. Are there any questions about this part of the lecture? So this is only skimming the surface, obviously, of some things that would require a deeper technical exposition to be properly understood. We only have a few hours. That gives the idea.
Excuse me.
Yeah.
When you show the idea that tau has to be identified after beta, you said that in the Euclidean space,
Yeah.
to be smooth at zero,
Yeah.
we need phi to be periodic.
Yeah.
But and so we have that tau has to be periodic in for some value of beta, so that when f goes to zero, the metric is smooth, right?
Yeah.
But I'm not seeing how these two are related, since in the Euclidean metric, r is still another coordinate, while here f is not.
No, but you could. So the analogy is, if you maybe this is the exact Euclidean metric.
Yes.
So my point was, at this level, if you take this metric on the plane with the tip, with the origin taken out,
Yes.
and you declare that phi is not 2 pi periodic but has some other periodicity, then this is still a flat metric on this punctured plane, but it does not have a smooth extension to the
Yes.
tip. Yeah? But the same would apply if you had a metric which was more like this, where f of r would be some would behave like something like this, and it would have to be continuous article 4. Yeah, so it's not really essential that this is precisely r squared. So it's about the behavior of this function. So it's the leading term which is relevant, and what's the coefficient here.
Okay.
Yeah. So since it only concerns the tip, there isn't really a problem how these guys behave.
Okay.
And also, it's not totally the same in this form. What I have not explained is that you have to first go to a different r coordinate here before you apply this. Go to the so-called tortoise coordinate. So, the same happens in de Sitter space also at the cosmological horizon. And so if you have the de Sitter method, moderately interesting, de Sitter space-time, so it looks like this, the Schwarzschild de Sitter space-time. So So here, as you can see in this picture, around here it's kind of the same. But then if you go far away, it's kind of quite different. And you're going to have the same problem that I described both here and there. So this is called the cosmological horizon. See, this with some other value, and these are plus. And you can see that you're going to have a problem here. So either you're going to make the metric, you make the periodicity of the time coordinate such that the analytic continuation is smooth here or there, but because the temperatures are not the same of the horizons in general, you can't have it both ways. So you can see also from this example that you're going to have a big problem with the Hartle-Hawking state in Schwarzschild space. The same kind of a problem appears in chaos systems as well. Nevertheless, the Hartle-Hawking state is an important state. So sometimes when people talk about it, they kind of get confused in their mind about Hawking radiation, because I'm not talking about that really. I still want to mention it. So sometimes, maybe also with a bit Stephen Hawking's fault, you can kind of maybe claim that the fact that a black hole Hawking radiates, you could maybe already see from the fact that the Hartle-Hawking state is a thermal state, and that's not right. So what is the Hartle-Hawking state? If you compute the stress energy tensor nearest chi, the expectation value, it will have no fluxes. No fluxes. Yeah. In a bath, you stand there. If you're not moving relative to the bath, there are no fluxes of anything. Yeah. So there is no Hawking radiation in the Hartle-Hawking state. It's in perfect thermal equilibrium. If you want to see the Hawking radiation, you'll see it in this state, because this is not in equilibrium, and this will have fluxes of stress energy, and that's the Hawking radiation. So I think one should kind of keep this separate in mind. Okay, so now building on this, this will, since so this, at any rate, leaving aside those important points, as many people have noted, after this suggests a relation with thermodynamics. So the thermodynamics kind of comes out of the geometry, either in this way or that way, and since thermodynamic concepts like entropy and so forth have, since Boltzmann explained and Shannon, have a connection with information, it suggests that there is a connection between black holes and information. That's the kind of case. So since this is the title of my lectures, I was going to now continue diving into quantum information and then connecting that with gravity and this kind of geometric ideas more towards the end. So one thing maybe I should say for more mathematically minded people, it's easy to say in words what the Rindler vacuum is supposed to be and what the Unruh state is supposed to be, and even doing some calculations, but really to define really those states, for a mathematician is very difficult actually, and it requires a lot of machinery that I can only skim the surface of this lecture. It's all possible. Okay, so now I want to explain some concepts of quantum information. And so whether you mention operator algebras or not, basically for a very large portion of this business, you're doing operator algebras. It's just maybe don't call it that way. And it's okay. Easier or whatever, but depends what you're used to or what you like, etc. Now the operator algebras are more relevant, particularly relevant in the QFT case, because the operator algebras are quite different in some ways, although similar in other ways, to the usual operator algebras of matrices that you encounter. So often this will manifest itself in some quantities diverging or some unusual properties of things, but I will try to be gentle and pretend first that we're dealing with operator algebras of matrices, and then maybe explain what's different if you do operator algebras of a different kind. Okay, so first of all, I should maybe not spend too much time on it. So classical probability. So you have some probability distribution Px. X is the label for the states. In following Shannon, the entropy is defined as the average of the surprise at seeing certain events, and the surprise is 1 over p, because the smaller p, the more surprised you should be at an event. It's very unlikely you're more surprised, and you should take log because you want the surprise to be additive. So if you win the lottery twice, which is already unlikely to win it once, you should be twice as surprised as winning it once, because it's independent. Yeah, so the drawings are independent. So that's why you need to take the log, because the log of a product is the sum of the logs. So this formula, minus px log x. So that's anyway how Shannon motivated it. And you can, of course, even if the system is classical, if you like, you can define always a density matrix by inventing just some orthonormal basis, and then if you do that, also minus trace of rho, and that's the formula. Now there is a related concept called the relative entropy. So really, the way that I explain it to myself is that nobody knows what is the true probability distribution of anything, even classically. We don't know it, we just have some opinion about it. So for instance, if you think of probability as relative frequency of occurrence, like a pole, nobody knows what the election outcome is going to be. We just have some opinions. Yeah, so some pollsters have this, the conservatives are doing better, the others say that socialists are doing better. They have some intention saying that, we don't know. So the more relevant concept, even classically, is that of the relative entropy. So the relative entropy is that suppose that we believe the probability distribution is Qx for some reason, but actually so we can then define something called the relative entropy, or the KL divergence, which our surprise, minus the actual surprise. So our surprise is log of 1 over q, because that's what we think the probability is. So we may think that some events are quite unlikely, so at seeing them we would be quite surprised, but maybe really they aren't that unlikely actually. So the average always is done, of course, with respect to the true probability distribution. Yeah? So this is then minus log 1 over p. And x. Now the quantum case. So here the words, here the classical and quantum, it's not really any difference. Though if you have relative entropies, there is no reason on Earth that why the actual density matrix and the density matrix that you assign to the system, there is no reason on Earth why they should commute. You just make some guess. So why not? They don't need to commute, and the moment P and the density matrices don't commute, the other density matrix may be some other orthonormal basis, which is just different from that orthonormal basis there, so they don't commute. Then there are different possible generalizations of this. And in fact, I talked to, when you talk to the quantum information theory people, it was not, I think, totally clear from the beginning what should be the right one. And in fact, there are just several. But to cut a long story short, I'm going to use the one that is due to the Japanese school, which is which, as you can easily see, will give you this one if the density matrices rho and sigma commute if they're with respect to the same orthonormal basis. But otherwise, you could write tons of other things. And so there is a long story why this one is pretty good, which I don't want to get into. But generally, should I explain that or maybe skip it? Maybe, yeah. So from a physicist, from a more thermodynamic viewpoint, so often you could think that maybe sigma it's the state that you think the system is in. Yeah, so that you should imagine. Often we say if we see a system, usually our guess is that it's in thermal equilibrium. Yeah, so this is the usual max entropy principle. So we just assign to it a Gibbs ensemble. So maybe we say something like this, and then it follows that the logarithm is minus beta h. And so you see that this term, this one trace minus rho sigma is just going to give you beta times rho h. you can think in some sense as this term here is minus the von Neumann entropy, because von Neumann entropy is minus trace rule of rho, and this term roughly is beta times E. So this means that this entropy is a bit like a free energy. Yes, you know, free energy is E minus Ts. Yeah? Up to 3 factors. Yeah. So maybe if that's maybe another way, another intuition, more thermodynamic for this thing is that it's the free energy. Okay. Right, now why this is special. So the point is, you could when rho and sigma don't commute, you can write tons of expressions that give the same classical expression here, just because of the ordering ambiguity of non-commuting operators. And so why this one is special? Satisfy something called monotonicity, or also called the data processing inequality. I think I'm going to take, maybe we could take a quick break, Eric, and use the chair. Could you take a quick break? Maybe 5 minutes, 10 minutes, 10 minutes, and start again at 11. And I'll explain the test.
Are there questions before the break?
We usually like that definition because it satisfies all those properties. The other generalizations for the non-commuting case have similar properties, they are different.
Is that a question or?
Yes.
Okay, well here's another property. So let me explain one alternative. So this is called, let me just review this one. This is called Araki, this is due to Araki. Araki. From this school. There's another one. I even myself have to look up. Okay, you can take the following thing. Try this one. Rho and sigma. It also looks pretty random. So minus the trace of rho and then log of rho inverse sigma inverse this one. So again, it formally is the same. So this, interestingly, also satisfies the monotonicity. And it's really different if sigma and rho don't commute. But what it doesn't. So there's one property that the quantum information theoretic people like, is that they call it an operational definition. So an operational definition is roughly this: you set up some quantum information theoretic task for which then the entropy, or E to the minus entropy, gives the asymptotic efficiency of attainable in an optimal strategy for this task. And so there is a very natural task for which this is the exponential of this gives the optimal achievable efficiency. And for this one, it's not known what such a task, or if there is, it's very elaborate and not very natural. Yeah. So since after all, the entropies, we perform certain tasks. Yeah. So just So that's how we kind of measure them. So it's this factor makes the hierarchy quite special from this. But also from operator algebraic viewpoint, both are okay. You define both. But there are many more. Yeah? So there are ones that do not satisfy the monotonicity. So if we put a different power here, if we put, then those are garbage. You will never.
Other questions? If not, we start again at 10. 11.